Yeah, good morning, everyone, at least morning in Cape Town. I wish I could be there, but thanks for having the talks and this talk online. So this is work done with my student, PhD student, Artur Mesquita. Okay, let's go. So what's wavelensing? I hope this will become more clear shortly why we call this wavelensing, but it's gravitational lensing in the regime of wave optics. So if you have a point lens and a point source, the magnification, it's frequency dependent. Okay, this is a hypergeometric function. We don't have a lot of intuition about what that means, but let's see in the regime of high frequencies, the expression is very simple. So this is the usual geometric optics, point lens, point source, and we have this oscillatory term. And what's important here is that the characteristic frequency can be written as a ratio between the Schwarzschild ratio, the Schwarzschild radius of the lens, divided by the wavelength, whatever wavelength we are observing. So we can see here in the plot what the magnification is as a function of this characteristic frequency. And for very short frequencies, for very long wavelengths, basically there is no lensing, magnification is equal 1. And when we go to higher frequencies, then there is this typical characteristic oscillatory behavior as a function of frequency. So this is the, I can now limit the function I have shown before with the sinus. So for high frequency, it's an excellent approximation. And for very for low frequencies, we have no magnifications. That's why, for example, we cannot use microlensing to probe the very low mass sub asteroid mass lenses as a probe of dark matter, because there is no lens. This has been discussed in several papers as a limit for how low mass you can go. I believe there are co-authors of this paper here and here also in this meeting. Of course, there is the finite source effect, but that's what hinders us to go to very low masses, right? So now the question is, can we turn this problem into an observable? So can you look here and use the wave optics as an observable, right? So that's what we are going to look for. Here is an example of a spectrum without magnification. Here is with this characteristic pattern of the wave effect of gravitational lensing. And this is what we see as an imprint in the spectrum. So the idea is, can we find this in spectra, right? The idea is not new. This has been proposed by Andrew Good more than 30 years ago. In the case of gamma ray bursts, the regime goes for very short angular separations, so what's called femton lensing. Here we look for this effect in all wavelengths, and we try to find possible real sources and lenses that could produce this effect. So the idea is to look for this pattern in the spectrum. So this depends on the impact parameter and the mass. That's where the magnification depends only on that, and the frequency, of course. And of course, depending on the instrument, we have a different wavelength coverage. So we consider a range of wavelength by a given spectroscopic instrument. We consider a given resolution, and then we impose some very simple detection conditions. So these detection conditions are on the amplitude of the oscillation. So we want to have a minimum amplitude such that it is detectable. For example, if we fix this at 10% amplitude, then this gets us to impact parameter below 6. We also are interested to be in this regime, so to the right, oscillatory regime. So we impose this condition on the maximum wavelength. And we impose the conditions to have at least a full oscillation in the spectrum within this range. And also, of course, we need these oscillations to be larger than the resolution. So this sets of four conditions, we impose constraints on this parameter space of mass and impact parameter, which of course depends on the instrument, right? So in the case of point source, point lens, this depends only on the lens mass and the impact parameter, besides once the instrument configurations is fixed. And the condition on resolution makes us to be on the left of this red line. The condition on being in the left of the peak and having a full oscillations makes us to be on the right of these lines. And the amplitude of oscillations means that we are below this blue line. So this region is where for a given instrument, for a given lens mass and impactometer, we will be able to detect wavelensing. But there is a caveat there that we are using a point lens. However, finite source effects are important. So we need to consider the total magnification of the finite source, which for incoherent source is just a mean. And we can see here in the plot that as we increase the size of the source, these oscillations, they get dampened. So we can see that for a point source, there is no damping. And as we increase, we have this damping. For example, with this red line, we have the magnification ends up being exactly the magnification in the geometric optics regime. So there are no oscillations. So actually, we have to consider these effects. And we consider the very same conditions as before. But now we impose that the amplitude of the oscillations, they need to be imposed on considering the finite source effect. The other conditions on the wavelength, range, and so on, they don't change because the position of the peaks is almost the same as with the point source. Okay, so imposing these conditions now, we have again that the detectability depends on the lens mass, on the impact parameter, but now it depends also on the source angular size relative to the angular Einstein radius, and of course on the instrument. So for example, let's consider one instrument in the radio with this wavelength range and this resolution that gives this kind of detectability plot, where now these colored curves are including the effect of finite source. And what is detectable is to the left of these curves. So as we go to larger source sizes, we have less detectability. And this is the limit for sources larger than this. You don't detect. We call this like an optimal limit. Any source smaller than this size will have the optimal detectability. There's no further constraint by considering the finite source. And this is the largest possible source. Above that, there is no detectability of this effect. So we consider a set of different instruments, just characteristic of each wavelength range. So on radio, submillimeter, infrared, optical, UV, X-ray, gamma rays. And then we make this kind of analysis to see what is the mass range where a lens would produce this observable that we call wavelensing pattern in the spectrum, right? And these are the minimum, the optimum, and the minimum sizes. So we see that fairly large sizes can be allowed. But ideally, sources would be very small so that we have the full region of detectability. And we see that the lens masses, they can be very high for very large wavelengths, of course. And if you go to very small wavelengths, of course, these are very light sources. But we can go from the range of many stellar masses to planetary masses to asteroid masses, depending on which wavelengths we go. So now so these do not necessarily need to be black holes, of course. So this can be real objects that we know that are there that can produce this wavelengthing pattern as long as we go to these larger wavelengths, not gamma rays. So the question is, are there real sources in distance ranges for which this effect can be detected? So we consider some sets of sources, like the local universe, let's call, within our galaxy or nearby galaxies. Consider sources as neutron stars, white dwarf, main sequence star, and the distant universe and high redshift universe. We consider sources like AGNs, kilonovas, supernova, gamma ray bursts, fast radio bursts. And so we take some typical distances of these objects and check if any of these objects would allow the observability of wavelensing in certain wavelength ranges. And the answer is yes. We in principle would be able to detect wavelensing even by main sequence stars if we could see them in the radio, let's say in Andromeda, for sources that are in our galaxy, right? Pulsars or neutron stars, they can produce wavelengthing in many wavelength ranges. And for the case of extragalactic sources, only kilonova and fast radio bursts would produce a long wavelength detectable effect, and at short wavelengths, only gamma ray bursts. So at gamma wavelengths, we will not be able to see wavelensing in any wavelengths, and it was actually looked for and never found. Okay, so under the present assumption, if we were able to see an event in the radio range, we could have stars, planets, or asteroids as a lens for producing wavelensing. In all these cases, the size, the physical size of the lens, be it a star or a asteroid, the physical size of the lens is much smaller than the Einstein radius. So this actually behaves. I mean, there is no obscuration. Actually, the rays would go through. I mean, we have a clear Einstein radius. We don't need to have black holes to produce this effect, right? Okay, so as this is seen in the spectrum, spectrum may have a finite exposure time. So if we think in the optical, for example, then we would have maybe minutes, hours exposure time to get the spectrum, and we need to consider some mean of this magnification, which is frequency dependent, but is also time dependent. So let's see what happens with this integrated effect if it's not destroyed by the integration time. So let's consider the case of a radio giant planet, stellar as the source, and this would give us a size that's well within the detectability regime of wavelensing. And that's what we get as when the exposure time as a fraction of the Einstein crossing time. So for very low exposure times, basically, there is no change in the pattern. But as we increase the exposure time, we have this kind of damping, which is not due to the finite source. Even for the infinitesimal sources, it's the same, just how they combine. And for very large exposure times compared or large to the Einstein time, these effects get quite weird. Maybe it's harder to detect. Okay, so for exposure times that are less than Einstein time, we are fine preserving this signal. So what are the takeaways? There is a new phenomenon that we refer to as wavelensing. We know that photometric light curves microlensing have been seen for decades. More recently, astrometric microlensing, direct imaging. And so there is this sort of new regime that has been talked about, mainly thinking about primordial black holes in gamma rays, but that could be extended to different wavelengths and looked for. An interesting thing is that there is this frequency depends on the impact parameter, which can be directly measured, and directly on the mass. So we break a traditional degeneracy in microlensing. There are direct measurements on the mass, and also we can measure the impact parameter and the source size by the damping effect. So that would provide complementary measurements to other microlensing observables. So in this work, what we do is to look for systematically for real distances between source, lens, and an observer, possible sources that would lead to the wavelensing effect in the spectrum for a given mass range of the lenses, right? And as we see, the lens does not need to be a black hole. So that's a very simple assumption about the detectability that we did for this study. Now the idea is to get a real spectra of objects at the signal and to see if we can recover the wavelensing signal. What we have shown here is that in principle it's possible to detect. Now, is it likely? We should consider the rates of production of these, the rates where we would have events that produce wavelensing for known lens and source populations, but also what we would expect, for example, for a population of dark matter in the form of primordial black holes or anything, how we can use the unobservability, if we don't see in real spectrum, the unobservability of these to set constraints on the lens population. So thank you very much. Of course, we look forward to detecting this at some point.
thought about the potential confusion limits for some of these wavelength measures? I would imagine, a radio survey of the Andromeda galaxy, there'd be a lot of potential sources there within the kind of beam.
Sorry, could you repeat the question a bit louder?
Yeah, so I'm just wondering if there is an issue with a confusion limit if you're observing a particular patch of sky to look for some of these signals. So you had like a radio survey of the Andromeda galaxy to look for these wavelensing events. There might be multiple such events and all sorts of other backgrounds within the same resolution element.
Yes, we should consider this for sure. We did not. We consider we have a single pristine spectrum of a single object. But of course, once we look at the real objects, we have to look at the density of them and if there is like contamination blending. Yes, thanks. That's something we didn't look for yet.